Hello. We've managed to make it most of the way through our recognition process for recognizing these polyhedra in the scenes that are captured using a range sensor point cloud. We've successfully matched a set of model planes to a set of data planes. And what we'd like to now do is look at the last two stages of that process. One is where we estimate the pose, which maps the model directly onto the data, and also a verification type process. And that's what we're going to look at in this lecture segment. So here's our data. Like the two-dimensional case, we're going to estimate the rotation first, and then we're going to do the translation. So here's our data. We have a set of matched model planes and data planes. And for each of those planes, we have a set of model normals and data normals, the surface normals of the planes. And for each of the model patches, we have a point on that patch, and each of the data patches, we also have a point on that patch. But in this case, we don't need to have the points be corresponding points. They just have to lie somewhere in that planar patch. We'll see how that works in a minute. Well, like I said, the first thing we want to do is estimate the rotation. And this is very similar to the estimating the rotation in the case of the two-dimensional, but here we're going to use a slightly more principled approach, again using this, looking for eigenvectors of a particular least squares type matrix. And the way we do this is, again, we say, well, we would like to find the rotation matrix R, which maps the model data onto the model vector onto the data vector. These are the surface normals. And I've got the dot here because it's not going to be exactly the right mapping on right here. And what we would like to do is sort of estimate a rotation matrix that sort of minimizes all of this approximation error. And here's a way of sort of stating that approximation error. We've got the rotation matrix rotating the model vector, and here's the data vector, and there's a little error between the two, and that's our least squares, and then we want to sum up all those errors, and we want to find the rotation matrix that minimizes all that sum. Well, we're going to do this in a slightly sort of different way, and the first is we're going to make the a rotation matrix, sort of a model matrix M, consisting of all the surface normals sort of stacked up right here, and then a data matrix consists of all the data surface normals, again stacked up in corresponding one-to-one. So for each model surface normal, there's the corresponding data surface normal. And then we want to take this matrix right here, and we do a singular value decomposition on it, which breaks it up into a couple of unitary matrices that have the eigenvectors in it, and then the eigenvalues along the diagonal right here. So it gives the U and the V matrix, which are the ones we want, and then it turns out that the rotation matrix that we're interested in that gives us the least square solution is this particular matrix right here. In order to do this, we sort of need to have at least 3 non-coplanar vectors amongst our data set right here, and we could actually do it with 2, but then there's a special case of where you get a mirror image. And so whenever you do this, you should probably also check to make sure you've not gotten the mirror image solution out of this. And if you do get the mirror image solution, there's an easy way to correct for it, but you can see that in the code itself rather than in the kind of the more sketch of the theory right here. Once we've estimated the rotation, we now want to estimate the translation. And again, we're going to use a least squares type approach. So let's assume that here's my data plane, and here's some sort of a point in that data plane, and here is my rotated model plane. So I've got my, I've applied this rotation that I've estimated already, and so here's the point, and then here's a kind of unknown translation vector that I don't know the value yet. That's what I want to solve for. And if everything was done correctly, then if we had the translation estimated correctly, then these two planes would be right on top of each other. The points themselves may not align, but there would be 0 distance between them. And that's the kind of error that we want to minimize in this particular least squares problem. Okay, so we want to minimize the perpendicular separation, that's that lambda for each of these corresponding planes. Okay, so lambda is the error, and we have all the errors, and we're going to square them and sum it up, so we have a least squares type problem. And what we want to do is find the translation vector which minimizes that. And it's sort of hidden in the middle of the formula here for the lambda that we don't need to kind of see all the details about, but if you look at the code you can kind of see a bit more. And the way we solve for this t vector is just the following process. We just take the data vectors and estimate a rotation and our points, and when you put it all together, this comes out as the solution right here for estimating that the least squares translation vector. And it works nice and easily and straightforwardly, and it's a few lines of MATLAB code to implement all of that. Once we have estimated the translation and rotation, then we can go into a verification stage. And this is where we want to check to see that the model whose shape and position we've estimated, when we project that model onto the actual data, it overlaps correctly. And given that we've got a lot of planes here at pretty much similar angles, sometimes we're going to get bad estimates out, and that's why we want to have that verification, just to make sure that we've got a good match. And we're going to use two different tests right here for this particular verification process. The first test says once we've estimated the rotated model normals, do they actually lie close to the data normals? And this is the test right here. We take the rotated model normal, dot product it with the data normal, and then look at the arc cosine of that. So that gives you the angle between those, and it should be a small angle, and hence we have that particular test. And similarly, we want to see that once we've estimated the translation, do all the planes lie close to each other? And that's what we look for here. So this is the ideal plane estimated for the data, and then we look and see if the model vertices after we applied the translation and rotation actually lie inside that plane, I guess within, again, a small tolerance. So we apply these tests for all of the model planes and normals and all of the model plane vertices, and if it passes all of the tests, then we have a verified model. So once we've done that, that gives us a way of sort of checking out our results. And here is an example of what we actually get with our set of range data that we've been looking at right here. So in the black lines right here are the model that we've had drawn on top of the range data using the estimated rotation and translation. And you can see that the lines lie up very closely with the edges. Now it turns out actually we got three solutions out of this. The model that we used only really just had the three corners of this. Didn't have any, it was only three surfaces. We didn't use the other two surfaces. But we did get three solutions because each of these angles are here at 90 degrees, and you can rotate them all around, and they still satisfy the verification constraints. So the model normals all line up with the data normals, and also the planes themselves are close to the data planes. And what we didn't do was we didn't model and verify, for example, the position of some of the other edges that lie on the block, and so we could have done that as well to be a final test, and then that would have probably gotten us down to just the single correctly matched pose for the object. But nonetheless, we've successfully recognized the block. We've got an accurate estimate of the alignment of the model to the data. Right, so what have we seen here? Well, we've seen really two stages. One is the pose estimation, and the other is the verification stage. And with pose estimation, we looked at a least squares type method for both the rotation and the translation. And both of these are quite straightforward given the kind of data that we have. And as we could see from the example, they're also both quite accurate. We also saw a verification stage that worked quite easily on the data. Not quite as strong as we would have liked, so it left us with three different solutions rather than one solution. But the three solutions that we did get are all perfectly reasonable given the constraints that we used for the verification. Thank you very much.